on Advanced Machine Learning and Signal Processing. We are about to begin the first session for today. On behalf of the Department of Computer Science, University of Calicut, and the organizing team, I welcome the resource person and all the participants. Dr. Umarani Jayaraman did her PhD from IIT Kanpur and started her career as an assistant professor of Indian Institute of Information Technology, Design and Manufacturing, IIT-DM, Kanchipuram, Chennai, whose research interests includes biometrics, pattern recognition, deep learning, digital image processing, human-computer interaction, etc. She serves as a reviewer for many international journals and different conferences happening around the globe. She is the co-author of a book on IT infrastructure and its management published by Tata McGraw-Hill and a number of journal publications in her credit. Currently, she is guiding 3 research scholars and 17 undergraduate students. On this Women's Day, I am proud to welcome an inspiring and active woman to this morning session of the two-day webinar, Advanced Machine Learning and Signal Processing, to handle the session on Generative Model with the Deep Learning. We welcome you, ma'am.
Thank you so much for your wonderful introduction. So let us, shall I start? Yeah. So is my screen visible? Am I audible? Yeah, okay, that's fine. Okay. That's fine. I have 41 participants. So this is just, I may ask questions, okay, whatever you know or whatever I'll strongly encourage everyone to interact with me. You can make use of chat or mic. Right now, camera is not attached in this desktop. At the end of the session, let me log in to my mobile ID so that I can answer your doubts if you have at the end of the session. Okay, so I highly recommend you to interact with me whenever I ask few questions. It's not to ensure to check the knowledge because everyone is learning, just to make an interaction with you all. So this is my request. Fine. So in today's session, the topic given for me is the deep generative modeling. It is a 2-day national webinar on advanced machine learning and signal processing. And first of all, I have to thank Professor Lajesh sir for inviting me this wonderful workshop and then given me an opportunity to interact with the young minds. So thank you, sir. So let me continue for today's topic. So the outline of this topic, since 2 session is given for me, so I may go in slow phase. Wherever you feel free, wherever you find it difficult, you can stop me at any point of time. We can take a break in between. Okay. So now you can stop me at 11 or 11:30. So that we can continue the next session. Maybe 10:15, 11:30 we can stop. So the auto encoder, we will touch upon what exactly the auto encoder and its applications in computer vision. And then the second half we will continue variational auto encoder. If time permits, we will talk about GAN. Let's see, depending on our speed. So I just made this talk is so fundamental. I mean, even though people or participants does not have any background about the machine learning or any kind of pattern recognition or any related things, people can also able to understand from my from this topic, generative modeling. For that, I just kept some 2-3 slides, which talks about very basics. Okay, from there onwards, I can take you to the actual topic that what we are going to discuss in today's morning session. Okay, so this one, the very first slide is just to give an insight. People, if you know about discriminative and generative model, it's just a recap. People who don't know about the background of machine learning, pattern recognition, for them it is just an introduction, so that it is easy to follow actual topic of mine in today's session. So let us explore what exactly the discriminative model and then generative model. So in discriminative model, it takes the Yeah. Yes, sir. I'm changing. Okay, one second. One second. Now it's visible? Oh, okay, okay, fine. So I just, this is my first slide. I have explained this outline of the talk. This is fine? Visible, right? Okay. So this I have given. Outline of my topic is autoencoder, its application in computer vision, variational autoencoder, and followed by GAN. So we are going to explore about the discriminative versus generative model. What exactly the discriminative model? Discriminative model takes the labeled data. Okay. So you know what is labeled data? If you don't know, let me explain. Like if at all you have taken some set of fruits, let's say apple and then banana. Okay. And then you take the samples that belongs to apple, so those samples, let's say S1, S2, S3, because all we are going to work on the samples that are given to us as an input. Okay, so S1, S2, S3, S4 are all the samples that belongs to the class apple. Similarly, some set of sample is given in the class of banana, S1, S2, S3, S4, and so on. Okay, so if you know that the sample is taken from a class or an apple, then apple is the label. Okay, similarly, if you know that this sample is come from this class which has some tag name or name of the class, then that is actually called as label. Okay, so in supervised learning, we work on the model of labeled data, because you train the model with the help of sample, and you know those samples are belongs to the label, or you know the sample is belongs to the particular class. That class is nothing but the label. Is that fine? Okay. So the next is that it tries to discriminate among different categories. Different categories, as I mentioned here, there are two categories that comes under fruit class, apple and then banana. So now if you want to discriminate a apple from a banana, then we want to, or we have to try to design a classifier which discriminates apple from the banana. Okay. Given an input image, the network tries to classify that input image is to one of the known categories. Suppose given an input image which is unseen, once the training is over, given an input image which is unseen or not seen by the network before, the network tries to classify that the input image to one of the known categories. This is actually the test case. Okay, in test cases what we want to perform is something like this, and these two are comes under training. Okay, so any machine learning consisting of two phase, one is called training, the other one is called the testing. Okay, unlike discriminative model, what does the generative model? In generative model, we expect that the network will be able to generate the new images based on the description which has been given. Okay, so now I have given so many things for you. Let me split. Okay, we expect that the network will able to generate the new images based on the
Excuse me,
description. Yeah.
will you please make the presentation full screen?
Okay. One second. Is it visible, ma'am? Is it visible?
Yes.
Full screen. Okay. Okay, fine. So in generative model, unlike the discriminative model, we expect that the network will be able to generate the new images based on the description which have been given. Okay. So there are two things. One is it has to generate the new images, and the set of description has to be given. Okay. Who is responsible to feed this set of description? That can be taken care by the machine itself. Okay, so this set of description machine itself tries to learn, and then it tries to extract the set of description. Based on that, it will try to generate the new images similar to the input images that we have given. So this is all about generative model. But if you are not able to follow, I will give you insights one by one. Okay. So the network tries to learn the set of description. As I mentioned that we have to feed the set of description. Okay. So the network tries to learn the set of description by itself. It tries to learn the description by itself to generate the new images, and hence this type of network is also called as generative model, or this type of model is also called as generative model. Okay. So continuing of discriminative and then generative model. In general, a discriminative model models the decision boundary between the classes. As we were mentioned earlier, you can see this. This is the discriminative model. You take the set of sample that are belongs to class, let's say blueberry, because it is given the blue dots. Okay, so blueberry, and these are the set of sample that are taken from the class banana. Okay, let's say BA, because both has the same label, blueberry and banana. How many samples have taken from blueberry? You can count. Sample 1, 2, 3, 4, 5, 6, 7. There are 7 samples whose samples have taken and then represented in two-dimensional feature. Okay. So two-dimensional feature, here we can talk about x1 and then x2. Let's say if we have given, these are actually dimension of the feature, and this the point x. Okay, when you take x1, any x1, let's say this is x1, this x1 can be represented with the help of two dimension right now, because it is easy to show for two dimension. Okay, but in general it can work for any number of dimension, where d increases 100,000, even more than that. Okay, people have tried to solve for higher dimensional data, but I'm not going to touch upon how to extract the features and what are the good feature selection, because that talks about the separate topic, separate domain, and people are working for the good selection of feature in the last era. But now, after introducing the deep learning conceptual idea, feature extraction also come under an integrated part of the classifier. Okay, when we were worked, feature extraction was the separate domain, and then classifier was the separate domain. Those who are working on the classifier does not have any idea how the feature was extracted, and some set of researcher works feature extraction without having an idea how the classifier will actually works. Okay, so this was the problem or barrier that we had faced before 2012. Okay, and after the boom of deep learning and then high computation power, and then availabilities of the tool make these barrier become so easier, so that the both feature extraction and the classification turns out to be as a single unit, so that those who are working on the machine learning or any deep learning or pattern recognition uh, research, no need to worry too much about the feature extraction part, because it's just done automatically by the machine. But I'm not going to touch upon that. But what exactly, whatever I'm going to discuss in case of discriminative and then generative model, it is completely different from that. Okay, in discriminative model, what we are trying to have is that we want to derive or have a mathematical expression for this kind of decision boundary. Okay, this is also called as design of classifier. Okay, the moment we say that we are going to design a classifier, the classifier could be anything. It could be linear, it could be non-linear. Okay, some popularly used linear and then non-linear classifier is the SVM, support vector machine. It just to try to solve for both. And before that, very basic um, classifier that tries to work based on the probability was the Bayes classifier. Bayes classifier also tries to solve for both the linear and the non-linear classifier. Okay, but the task whatever I have given is an example that comes under the discriminative model. Okay. I have given two example. One is SVM, and then I have also given Bayes classifier. Okay. These two are an example that comes under the discriminative model. So the job of the discriminative model is to have a decision boundary of something like this. If it is linearly separable, we have to get a mathematical equation for that. Okay. So that is the job of the discriminative model. So that what is the job? Once we have derived this decision boundary, what is the job? The job is that if at all any unknown or unseen data is given for the network, okay, the network's job is to try to classify that unknown pattern into one of its classes, whether it is belongs to blueberry or banana. Okay. For example, let's say an unknown feature vector after extracting the feature x1, x2, let's say if it lies somewhere over here. Now, what the classifier does once we have the decision boundary, it just simply substitute this value x1, x2 on the mathematical equation. Okay. Suppose for simplicity, let us have the equation of a line. Okay. So then equation of a line is the simplest one if at all the classes are linearly separable. Then you can have a straight line, right? So we can substitute those value x1, x2 into the equation of this straight line. Then you can compute what is that? But you have a weight vector. I'm not going to talk about in detail. You just have, let's say this is the g of x. Okay, where x is nothing but x is the capital X consisting of, after substituting the value x1, x2, once you computed or substituted, it can give you the three possible value. The one is g of x may turns out to be 0. The other one is g of x is greater than 0. And the third one is g of x is less than 0. Okay. So one of the three cases may occur. Okay. When we say that g of x is 0, actually the point lies on the decision boundary. Okay. In that case, we are, or the network is not able to take a decision whether the given point may belongs to blueberry or banana. So this is of no use, because when we uh, train the model, if it gives 0, meaning that we are not able to take a decision. Okay. But that happens very rarely. And these two cases may happen depending on the value of x. Okay, where x consisting of x1, x2. If g of x is greater than 0, let's say that lies the upper part of the plane. Okay, if a plane is given, if this is divided by some if the feature space is given, if that is divided by a straight line, let's say something like this divides the whole space into two half. Okay, and this half is greater than, lie other side of that g of x is greater than 0, and the below side of the line is less than 0. So we can consider in that way. After substituting this value here, if that value turns out to be greater than 0, means it lies this part, upper part, and then we can say that the unknown data belongs to the class banana. Okay. The third one, if that value g of x is less than 0, then that means it lies the lower part of this space. Then we can say that the given unseen data is belongs to the class blueberry. So this is how we have designed a classifier, and existing classifier such as SVM, Bayes classifier, then perceptron. Okay, the very beginning model for the neural network, perceptron, and sometimes the neural networks all comes under the discriminative model. So this is all about discriminative model. Now, when we talk about generative model, okay, let me erase everything so that it will be clear. Okay. So the next part is that generative model. Generative model explicitly model the actual distribution of each class. Now you can have a look. This is all about the generative model. Now, as you can see that here there is no decision boundary. Okay, we are not going to discriminate the given classes with the help of decision boundary. Instead, we try to form the distribution that fits with the sample data. Is that fine? So the same set of sample is given, and then it tries to fit the probability distribution for each of the class. Okay. Okay, using that, what we are going to do? So it is going to do, it tries to generate. So this triangle, right? It's try to generate a new images which is actually not existing in reality, but we are trying to generate that new one based on the sample that it is given in within the distribution. Okay, I hope the idea is clear. Similarly, if you want to generate after finding the probability distribution, you can also find uh, some new images that fits within this probability distribution, so that this exactly looks like a banana. Okay, similarly this will exactly looks like a blueberry. Okay, if you are generating other than blueberry, then there is no use. Fine, because the whole idea is to generate the sample that looks very similar to the input images that we are taken. So there are applications. One is the data augmentation. Okay, I'll talk about the application later. But I can give you the quick insight. What is that data augmentation? For example, if you have given some problem to work on classification of, let's say, mm, classification of any disease. Okay, but most of the real time applications, we have only normal data. Okay, a particular disease have very few people only get affected, and only those affected people go to the hospital and take some MRI images and so on. So normally we get the diseased data comparatively lesser than the normal data, which has enormously available. Okay, so in that situations, uh, no matter whatever you give a training to the network, it will always try to classify the deceased data also as a normal data, because you have trained the neural network with lots of normal data. So that is of no use, right? So we generally make the balance, we generally make the network, first of all, make the data balanced. Okay, so that is called uh, balanced data. So if at all you do not have sufficient data, wherever you find, or where in whichever the application, if you have lack of data, first of all, people follow the upsampling the data. Okay, for in that situation, people try to make use of the data augmentation. So first of all, they try to produce as many images very similar to the input images and make the data balance, and then you can proceed for the training of neural network. Okay, but this is most crucial in case of medical images, because in medical images, when you are trying to generate the new data, it has some disadvantages, but other than medical data, it has really good efficient. So we will talk about that part later. But I have given one example where this generative model would be so useful. Okay, so that I have given enough motivation. Why do we talk about the generative model? Fine. Okay. So I hope everybody has understood that in generative model, we are trying to generate the similar data which tries to fit the probability distribution. Okay. In final, both of them is predicting the class probability only. Okay, but one is doing the other way, the other one is doing in different way, but in both, if you can see that both are trying to predict the class, or what we can say is the conditional probability. So what exactly the conditional probability? For example, if the features are given to you, so feature is nothing but, as I said in my example, which was x, this x consisting of x1 x2. If the feature is given, we have to predict in which of the class it belongs to. Let's say Ci. Okay. So now this probability is known as class conditional probability. Here I have given like this. Given set of feature, we have to predict in which of the class it belongs to. I have taken the class as fruit, but if I have taken the class as animal consisting of cat, rat, or something else, I have given an example like this. But what is this? You know the feature of an unseen data. Okay. You measure that. Once you measure, you know this. Based on it, you try to estimate what is the probability that it may goes to the classes consisting of Ci classes, where I ranges from 1, 2, 3 up to C. Okay. Let's say there are C number of classes. In this case, only 2 classes. If you have taken the fruits from 5 classes, let's say blueberry, banana, apple, and then what is that? Oranges, and then jackfruit, and so on. So all these 5 different fruits is coming or represented as 5 different class. So you just try to estimate in which of the class it may belongs to. Obviously, if you take a probability, you should get the higher probability. Okay, you just compare with all the classes. What is the probability that it belongs to class 1? Let's say C1, C2, C3, C4, C5, and you just try to assign that feature vector which is the class which has the higher probability. So that is the simplest one. All it tries to do this conditional probability, but everything tries to do in its own way. So that is where it differs. But these two model tries to predict the or predicting the conditional probability based on the feature given. Okay. Okay, fine. So, but both models learn these things in different way. Okay, different probabilities. It make use of different probabilities to do this task. Fine. So I'll stop after taking some couple of slides to address your question. Okay. So okay, fine. So whatever we learned is about the difference between the discriminative and the generative model. A generative model learns the joint probability distribution. Okay. As I mentioned that it tries to learn the two different probabilities. In generative model, what we saw is that it tries to learn the joint probability distribution which is given by P of x comma y. Okay. In joint probability, it predicts the class conditional probability with the help of Bayes theorem. Fine. Uh, Bayes classifier, I hope everybody understand that. As I said that given feature vector x, if you want to predict in which of the class it belongs to, this is posteriori probability. Okay. This can be solved with the help of class conditional probability uh, P of x given by Ci. This is conditional, I mean, probability class conditional density function, you can say that, and a priori probability, which is P of x, sorry, a priori probability, which is P of Ci, from which class it belongs to, divided by likelihood, which is nothing but P of x. Okay. So this is posteriori probability, this is a priori probability, this is evidence, and this is class conditional probability. This is all about Bayes theorem. So some example that comes under generative model. Okay, some example that comes under generative model. Uh, Generative model is the naive Bayes classifier and Bayesian network, and then HMM. HMM stands for hidden Markov model. Okay, so all these try to predict the class conditional probability with the help of Bayes theorem, but it tries to work on the joint probability distribution. Okay. Now coming to the discriminative model, a discriminative model learns the conditional probability distribution directly. So as I given here, right? You know feature vector which is x, y is nothing but the class label. So this I can straight away write this P of Ci. Y is nothing but the class label, or you can say that class, in which of the class it belongs to, and X. So now you can see the sum of the examples that comes under the discriminative model, as I have given earlier. SVM and then logistic regression all comes under the discriminative model. Okay. Both of these models were generally used in supervised learning problem. Okay. So Bayes classifier also comes under supervised learning, and then Bayesian network, HMM, everything. Okay. Although generative model follows different way and then discriminative model follows different way, everything comes under the supervised learning, meaning you know the class label. Fine. So far, whatever we have discussed, okay, so far we have discussed only the supervised learning. Okay. In supervised learning, what you have the information which is nothing. The data can be represented into tuple. One is the feature or feature vector, which is X, and you also have the label, class label. So X and Y, you know, X is the data, Y is the label. X is actually feature vector, okay, and Y is the label, class label. And given these two, the goal is to learn the mapping function. So what exactly you want to learn? You know the feature vector. Given the feature vector, you try to classify in which of the class it may belongs to. Okay, this is nothing but as I have given CI, number of classes. Okay, so what are the models or what are the tasks that comes under supervised learning? So many applications that solves with the help of supervised learning: classification model, regression model, object detection, segmentation, all comes under supervised learning. Meaning you know the class label of that particular feature which has been extracted from the images. Is that fine? Now today, so in my topic, whatever I'm going to discuss, that comes under unsupervised learning. Okay. Unsupervised learning takes only the data in the form of X. So what you have only the feature vector. What you don't have Y. Okay, X is data and we don't have label. And the goal is to learn the hidden or underlying structure of the data. Okay, whatever the sample that is given, you make use of those sample and then try to learn what are the underlying structure of the data. Okay, and then you try to generate the images which are very similar to the samples. Fine. And people worked already, that comes under unsupervised learning, is clustering. In clustering, you try to group the similar set of items or similar set of data where it shares the common properties. So that comes under clustering. K means clustering. Many types of clustering that you know already comes under the unsupervised learning. And the very popularly mechanism that you use, okay, feature reduction or dimensionality reduction before you actually do the training, also comes under unsupervised learning. Okay, and today whatever I'm going to discuss, okay, this comes under the unsupervised learning. So what we are going to discuss is unsupervised learning. So let me summarize whatever I have given to you right now. We were discussed discriminative model and then generative model. So far, I said that both discriminative and generative model make use of supervised learning. I have also introduced what exactly the unsupervised learning. And today's topic, although that it comes under generative model that we are going to work on the unsupervised mode. Okay, unsupervised learning. So I'll continue uh, about unsupervised learning. Generative model make use of unsupervised learning. One important note, see, here also we make use of the sample. Okay, both in the supervised learning we make use of samples. Here so let me represent, these are the samples, number of samples. In unsupervised learning also you make use of sample, but what is the difference? You know that these samples have taken from this class, that you know, but you don't know that from which of the class the samples have taken, that you don't know. But in both the model, supervised and then unsupervised learning, it makes use of sample only. Okay. So with this, let me stop for quick question. Let me address here if there is any question. Let me discuss. So you feel free to ask your doubt, question, any doubt. You can type in chat or you can unmute and then ask. Is it clear? First of all, any doubt? Mic is allowed, no, sir? For the participants? Yeah, okay. Yes, yes. Is it clear? First of all, if it is clear, can you all type yes? Just give some, type yes if it is clear. Everyone. I received one. It's good. Okay, fine. Can you all type? Yeah, quickly. At least I can get good. I have given, there are 59 participants. Quickly type. Yeah. Okay, if you have any doubt. I mean, this, up to this, you must have explored from attending several times. Okay, I hope this is clear, because whatever I have told right now up to this is already known. Okay, if someone is very new to this program, especially for machine learning, for them it might be useful. For the rest of people, it's just a quick recap. Okay, if there is no doubt, shall I proceed? Type yes. Okay, yeah. Okay, fine. So now let us talk about, as I said, that what we are going to discuss is comes under unsupervised learning. In unsupervised learning also, we make use of the sample, but we don't have the label. Okay, and in generative modeling is one example of unsupervised learning. Okay, there are so many things that comes under unsupervised learning. I have given an insight: clustering, feature extraction, feature reduction, dimensionality reduction. All are examples of unsupervised learning. Generative modeling is one such example, and there could be many examples that comes under unsupervised learning. So what is the goal? What is the goal of generative modeling? The goal is take as input training samples from some distribution. So you know the, as I given the insights, that you know the set of distribution. Okay, how do you know the set of distribution? For that you make use of sample. Fine, and you know the distribution of the data, and learn a model that represents that distribution. So you are going to representing that distribution in some way. Okay, if this is not clear, you wait until our topic is completing. And this can be achieved in two ways. Okay, the goal is to estimate, or what is that, learn the distribution of data. That can be achieved in two ways. One is the density estimation, the other one is the sample generation. Okay, although we are going to follow the sample generation, this is of our goal. You should also try to get an idea what exactly the density estimation given the sample. Now you can make use of this samples. So what this graph tries to do this? Can anyone give me a quick insight? What are these red color and what you're trying to do in density estimation? What is your goal? You want to learn the distribution of the data that are come from the sample, or you can make use of sample and then tries to learn the distribution of the data. So what exactly the samples here? Okay, so these are the samples. So you make use of these samples and use the samples to fit this probability distribution. Normally we will make use of the distribution called Gaussian. which comes under normal distribution, because most of the practical applications consisting of noisy data, and then it should work in the uncertainty mode. So normal distribution is the best way of representing from the samples that we have. Is that fine? So what we are trying to do, generative model, it tries to estimate the probability distribution. Generative model, one way is the density estimation, and then use these density estimation to solve the posteriori probability, which I have given. Okay, that is one way. The other way is that you can generate the sample generation out of this probability density function that we try to learn. That is our goal of today's topic. Okay, fine. Now, if that is clear, now let us continue. Generative modeling, sample generation. What exactly sample generation mean? Okay, sample generation means we are generating the synthetic sample. As I said that synthetic samples or synthetic examples are the samples which are not existing in reality. Okay, synthetic, fine. So in order to generate these synthetic sample, for that you have to make use of the actual images, which is also called as input sample, and then we do training. So training happens with the help of actual data. Okay, which is nothing but P of data x. P of data x is the actual distribution, probability distribution that has been generated from the actual image. Use this to generate probability of x. Okay, you are trying to generate this out of P data of x. So how can we learn P model of x? How can we learn P model of x similar to P data of x? That should look very similar to P data of x, which is nothing but true data distribution. This is all about the generative modeling. Okay, so these things summarizes concretely what are the key principles behind the generative model. So till now I just make use of these slides to give an insight about what exactly the generative model. Okay, so these things summarizes concretely what are the key principles behind the generative modeling. Okay, now let us go to the actual topic. Generative model. Generative modeling is also called as latent variable models. Okay, which is nothing but auto encoders. So that is the core conceptual idea of the topic. So two classes of generative models. There are two different classes that comes under generative model. One is autoencoder and variational autoencoder. Now you can see that the structurally these two are different. Okay, so this is so important. Autoencoder and variational autoencoder structurally match something like this. Okay, we don't know what are these things, now it is hidden, but what you know, this is an input and this is the latent variable. Let me talk about everything in detail. And this one is generated, it is not generated images, it is not newly generating, it is trying to reconstruct the original image back. So all everything I'll explain in detail. But you just to know input image is going to reduce. Okay. So you can think of this is the size of the image in original and this is in the reduced form. And again something is doing to reproduce in its original form, which exactly looks like the input image. So let's say this is x hat and then x. Okay, and it is trying to do something. What does that we will explain one by one. Okay, again it is from the reduced to size, it just transform into the original size that looks exactly to the x size. Okay, now when we talk about other model, okay, there are two model. One I have given this autoencoder and then variational autoencoder. The other one is the generative adversarial network. Now you can see this is GAN model. Okay, So now here GAN model structural is different. Now this is the generative model. Okay, so you can see this also does something, but generative model generate the samples, that is fake sample, and there will be a discriminator. The job of discriminator, whatever the fake that it has been generated, let's say x hat, it tries to give a comparison with the actual images and try to reject saying that it is a fake images. So as long as it tries to reject and that feedback is given to the generative model, it will try to give, or it will try to generate the images at some point of time. It seems that the difference between x hat and then x is as minimum as possible. So some point of time discriminator cannot able to really distinguish that this is the synthetic image. Okay, so that is the power of generative uh, generative what is that step, generate, which tries to generate which looks exactly similar to x. So this conceptual idea is completely different, but although the purpose okay, so whatever the idea that we make use of here is also makes use of here. So that is all about GAN model. Okay, so these two model are comes under generative model. Now make a note, these two model comes under unsupervised learning. I'm repeatedly saying here because you should not forget that. Okay, unsupervised learning. In unsupervised learning, we are giving only the sample. Okay, we are not giving the label. So y is not given. So y is missing. Okay, fine. So both of these models are classes of latent variable model. Okay, both these models comes under latent variable model. For that, let us try to explore what do you mean by latent variable, or what do you mean by latent variable models. Okay, so now let me introduce latent variable. Okay, why these are called latent variable model? What is actually called latent? Now let us understand that. Okay, have you seen this kind of picture ever before? Participants, have you seen this kind of picture ever before? Yes, no? Type it in the chat. Yes. If you have seen, yes. If you have seen, not seen, type no. Type your, I'm looking at your chat. Yes, no, have you seen this? Okay, this picture ever before? No. Okay, okay, fine. So most of you typing no. Oh, okay. This picture I make use of to make you understand what exactly the latent variable, nothing else. But I can give you the insight to understand better what exactly the latent variable. Because if I read the mathematical definition, nobody able to follow. Okay, so I'll make use of this picture to explain what the latent variable. Now this picture is taken from the book name called, the name of the book is Myth of the Cave. Okay, Myth of the Cave. I don't remember the author name now, I forgot. But that has been written by the author, right? From that book this picture has been taken. Now you can see that I'll explain what are the things that you can see here. Now this is like a cave, okay, and some set of people are sitting here, which is the other side of the wall. This is the wall, okay, this is the wall, and set of people are given, a set of people are sitting here. These people are prisoners actually, okay, those who have done something outside, and they'll get punished. Okay, those people are kept in the, what is prison. Actually prison is nothing but this is the cave. Okay, and these people are sitting the other side of the wall, are all prisoners. Okay, and you can see that some sequence of people or set of people actually holding the object. Okay, these object are getting projected, or the shadow of these actual object is getting projected on the wall. Okay, those prisoners are allowed to see only in the forward direction. Okay, if they turn back, then they'll get punishment. Okay, they are not supposed to turn at the back side. Okay, they are not supposed to turn at the back side. The only thing is that they could able to see only in the forward direction, whatever they could see on the uh, in front of them. Okay, and these are getting projected by holding the actual object. Actual object is kept in front of the fire. So this is a fire. Okay, otherwise the shadow cannot be produced, right? So these set of people actually holding the object, which is original or actual object, which is kept in front of the fire. Because of this fire, this is getting projected onto the front of the wall. Okay, and for the prisoners, these are the actual object for them. Okay, actually they don't have an idea these are the shadow that are actually projected from something else. Okay, and they could make use of these shadow variable. They can name it and then they can measure it. Only these things are allowed for these prisoners. Now these shadow variable which are actually produced from the hidden variable, right? What are the hidden? It's not a hidden variable, hidden object or the actual object is called the latent. Now I can name it variable. Okay, okay, this is called latent variable. Okay, so now let me read now. Actually, what I'm saying is that the hidden object for the prisoner is the latent variable. What object are hidden? For this prisoner, these objects are hidden. Okay, only they can look forward the or they can able to observe only the shadow object. What it is hidden for them? The actual object. Okay, the hidden object is actually called as latent object. Now let me replace the word object by the variable. Okay, the hidden variable that actually existing in the actual or original objects are called the latent variable. Now let me read this so that you can better understand. So the latent variables here are like the objects that they cannot directly observe. So these people they cannot directly observe, but are the ones that are informing or generating these shadows. Actually, these shadows are generated because of the original object. Actually, this original object is hidden for the prisoner. These hidden objects are called the latent objects. Okay, in this case, these are called the latent variable. I hope this able to understand better what exactly the latent variable. But this figure is trying to keep a relation between the latent variable to understand better. Okay, nothing explanation is given. Just to I have make use of to understand you better. Okay, now let us read the actual definition that is given from the Wikipedia. Okay, so let me read, and then you can able to relate whatever the story that I have explained to you. Okay, in this case, the observable or the shadow that the prisoners see generated from the hidden variables, which are called latent variable. So as I have given some insights, maybe it is easy to follow. Okay, so the observable or the shadow, what you can observable, what prisoners can observable, the shadow, right? That the prisoners see generated from the hidden variables. Hidden variables are nothing but this one, hidden objects, which are called the latent variable. So actually these are called the latent variable. Now, actual definition, the variables that are not directly observable, but that are true explanatory factors that are creating the observable variable. Okay, they can able to create the observable variable or called the latent variable. Is that fine? This is the actual definition given from the Wikipedia, but nobody able to follow by just simply reading. What you can understand is that from looking at the picture, you can understand that the hidden variable or the latent variable. Now let me explain what exactly the hidden variable by giving this example. Okay. Now everybody can see my PPT, right? So you can read this. Big animal has 4 legs, big ears, long trunk, a pair of tusks. Pair of tusk. Okay. So given these set of information, so these are description, right? Given this set of description, is it not easy to identify what type of dash we are talking about? Dash means animal. So I have given the clue animal. Is it not easy to talk about what type of animal it is? Can anyone tell me the answer in your chat? Or you can unmute and then tell me. What is the answer? The set of all description given. Having explored this set of description, is it not easy to find out what animal we are talking about? Okay, let's see. Elephant. Okay, elephant. Okay, good. So now you understood the insight, right? So elephant, very good. Because it is easy, set of all description is given. Now you see, we are talking about an animal elephant. Now, do you know that the set of all description from where it has actually originated? Okay, actually these are hidden. These hidden variable actually existing in this picture. Okay, for us, this is the output. It's like we are the prisoner, we can able to see only the shadow. This is the shadow. But for us, actual variable which are hidden are called these things. Okay, because we already learned from our childhood that an elephant is a big animal. It has 4 legs, big ears, long trunk, pair of tusks. This we already know, actually hidden, right? So these are called latent variables. Okay, these are called latent variable. Can you able to see these variable here? Actually no, right? But these are actually hidden. This is like a shadow for us. Okay, this is like a shadow for us, and these are the variables which is actually hidden, that has been actually originated from the original objects, are called the latent variable. I hope I have conveyed this topic or idea in a better way. Understood, right? So the description known as the set of description is known as the latent variable. All these latent variable put together becomes a latent vector. Okay, so the job of network is try to learn the set of description on its own. In the beginning of my lecture, I have given generative model tries to learn this latent variable by looking at the, or when we give an input image as an input to the generative model, it tries to learn the set of description. This set of description also known as latent variable on its own. Okay, so is that part clear? We have actually got the insights of generative model. Okay, now let us talk about more in detail. As I have given in the beginning, auto encoder. Auto encoder, just I have replaced that input layer. Okay, so with some image. Okay, so what is a latent variable? It maps an input image via an encoder to a deterministic latent code. So can you tell me what is the latent variable here? Can you read all this? Okay, so by looking at the picture, what you can say are the latent variable, which actually hidden. By looking at this picture, I can say that it is a male, and he has a beard, and he is smiling, and he has a black hair, and then skin color is somewhat skin tone is given. Now you see, smile is given high probability. All I can measure. Okay, so variable is nothing but the measurable value, and all these values can be measured, and then you can give in the form of one or more latent variable, form the latent vector. Is that fine? So now when I'm looking at this picture, without knowing, you can able to extract this set of descriptions. Okay, smile 0.99, skin tone 0.85, gender 0.8. Okay, 0.8 means with high probability we can say that he is a male. And then beard 0.75, glasses 0.001. He is not wearing any glasses. And then hair color is 0.68. Now you can able to generate by looking at the picture. As natural intelligence, any human can able to generate this type of description. But how do we make to learn the machine by itself to generate or to learn all these latent variable on its own? That is the job of autoencoder. Is that fine? Now, what exactly autoencoder does? To learn this latent variable on its own, actually these latent variable are hidden, or you can say that these are the shadow, and we are getting the actual variable which are hidden from the shadow variable. Okay, so it maps an input image via an encoder to a deterministic latent code. Fine. I have talked about only this encoder part. Now you can also have a look of decoder. Okay, so decoder part, decoder maps the latent code to reconstruct the input image. Why do you want to reconstruct? That we will see later. So what you can able to follow is that there is a two phase. One is the encoder phase followed by decoder phase. The encoder does the given input image, let's say X, it tries to map into the latent variable, which is Z. Now you can make a note, this Z is very, very lesser as compared to the original input size. So these are nothing but the size. This is in terms of dimension. This is also in terms of dimension. The dimension here, the size of the, what is that? Size of the image. Now here you can measure the size in terms of feature vector. Okay. So there is one step which does encoder, and other step which does the reverse, decoder. Decoder takes the mapped Z. So the job is to encoder to generate Z. The job of decoder, it takes Z and then try to reconstruct the X hat. Okay, it is just a reconstructed image that has been taken out of this description. Now you see whether the reconstructed image is same as the original image. If the reconstructed image is same as original image, then the job of autoencoder or the autoencoder does the correct job. If it is not able to reproduce other than the input image, if let's say the noise is more by the decoder, then the autoencoder does not complete its job correctly. So what it says, it has to give an input feedback to the encoder. Say I'm not able to reproduce what exactly I could see the input images. So just try to, and so then autoencoder does the things again. Okay, until this process repeats until and unless the difference between the X hat reconstructed image and the input image is input image is not X hat and then X, the difference is as minimum as possible. You can say that the error is as minimum as possible. When can you say an error is minimum? When you have the reconstructed image is same as the input image, which is X. Okay, as long as the difference is error difference is minimum, the autoencoder tries to produce different kind of set of description, and it stops where the set of description is tries to able to reconstruct the image which looks very similar to the input image. And in that case we can say that the autoencoder has extracted the right set of definitions or set of description. Is that fine? Okay, let me take 2 minutes. Keep thinking. If you have any doubt, you just ask me. I'll 1 minute. Is there any doubt? Shall I proceed? Is it clear? Okay, fine. So we understood what exactly the autoencoder wants to do. Okay, as I said that the set of description, it tries to extract on its own. Okay, hence the name autoencoder. Fine. So I think let me read whatever I have given. So can we learn the true explanatory factors, which is nothing but the latent variable, from only observed data? The question is that for us, the observed data is nothing but the shadow. Okay. So observed data, or I can replace that shadow by the observable data. This is for us, this is the observable data. For the network also, the data that we feed is the observable data. Is it possible, or can we learn the true explanatory factors, which is nothing but the latent variable, from only observed data? So that's the interesting part, because unless it tries to learn the latent variable um, correctly, it is not able to reconstruct the back. It is not able to reconstruct the image back. Okay, I can say you why this decoder part is required. Fine. At the end, I could say that. So first, we will discuss simple and foundational generative model, okay, which tries to build up this latent variable representation by actually self-encoding the input, and these models are known as autoencoder. So it tries to learn, or it tries to actually self-encoding the input, and these models are known as autoencoders. Okay. Now let me give autoencoders. Autoencoders, it encodes itself, and there are one important model that comes under complete autoencoder. I'll tell you the difference at the end. Okay. So what exactly the autoencoders? Autoencoders comes under unsupervised model. Okay. You can make a note that nowhere we were given the label of the data. Here also. So what we have given only the observable data. Okay. I have not mentioned the name of the person here. Okay. Uh, so I have not mentioned the name of the person, which is actually the label, or I did not mention any the gender. If I can give you the gender that is belongs to a male, that is also called as a label, but I did not mention any label. uh, with that, it tries to extract the set of description. So that set of description is actually the latent variable. So let us not use set of description henceforth. So we will make use of latent variables. Okay. So unsupervised approach for learning a lower dimensional feature representations from unlabeled training data. So this is what the goal. So it is lower dimensional feature representation. See, note down that is more important. This Z is lower dimensional representation of the given input image, which is X. Okay, this Z is very, very less as compared to the input image X. Okay, from the unlabeled training data. Encoder, what is the job of encoder? Encoder learns mapping from the data, which is X, to the lower dimensional space, which is Z. So, what I mean, what an encoder does, it takes an input image X and then tries to map Z, and at the same time, this Z should be represented in lower dimension. So that is the whole task. That is what you can see that it is the trapezoidal shape. The meaning is that as you move with one or more number of layers, the dimension keep on reduces. So now, as I said that I have to talk about, or I have to reveal what exactly the trapezoidal consisting of. Okay. So this I'm trying to, okay. So this part we are trying to reveal that. So what is that consisting of? It consisting of input layer. This is output layer. And what are these layers? Can anyone tell me what are these layers? Oh, hidden layer. Okay. So what are these layer? Hidden layer. So I can have one or more number of hidden layers. Fine. So now you can see there are three hidden layers. 1, 2, 3. Okay. So what is the role of this hidden layer? Okay. Now you can think of this whole network is nothing but the convolutional neural network. Okay. I hope you have an idea about the convolutional neural network. Convolutional neural network consisting of sequence of steps, convolution on max pool and then min pool, you are choosing only the maximum value out of the window that we have. The dimension keeps on reduces. Is that fine? So here I can say that this is all about convolutional neural network. You can apply a sequence of max pooling. All about the autoencoder tries to do on its own. That is more important. Nobody does. Okay, the machine or the network itself does on its own. So encoder learns mapping from the data x to a lower dimensional space, which is z. Okay. Now, an interesting question. Why do we care about lower dimensional z? Can anyone give your answers? Why do we care about a lower dimensional representation, which is z? Just type your answer in the chat. Why do we care, or why do we want the z, which is nothing but the latent variable? Okay, the z is nothing but the latent variable. Why do we want that? Whatever you know, you can share. So no matter it is correct answer, it should be correct. So I said in the beginning, I may ask some question just to make an interaction. Okay. So just type your answer, or you can unmute and then give me your insights. Why do we care about this lower dimensional representation z, which is nothing but the latent variable? Yeah. Nobody? Okay. So why do we want? You can see that since the dimension is as minimum as possible, it reduces the computational time. Okay, where does that computational time reduces? During your training. Okay, okay, fine, sir. I'll continue. So you can say that if the dimension get reduced, the it minimizes the cost for training. Okay, so that is where it is important, because in convolutional neural network, the number of weights, okay, hyperparameter is depending on the weight vector. Okay, w transpose multiplied by x. So if the weight vector is as minimum as possible, you can speed up your computation, or you can speed up the training process. Otherwise it will get slower and slower if the weight vector is large. Okay, so why do we care about that? I'll give you, then I can stop. So to find the most meaningful and then rich information that are really contributing to what is underlying this data distribution. As I said that we want to represent the underlying data distribution. How do you represent? With the help of this z. Okay, this help of z, you are representing the underlying data. So pixel or incredibly sparse representation of the images. Now when you see this kind of image, you can see that this consisting of lots of background. The background images is nothing but the lots of what is that background value is nothing but 255, and then sorry, background information which is represented is white pixel which has the value 255, and this black color value is represented by 0. So you have the useful information that are represented only these two consisting of this, and you can see that the lots of information which is not actually useful for us is the background portion, and which is sparse. Okay, so pixels are incredibly sparse representation of images, and often we don't need all that information. Okay, we don't want, which is actually not useful for us. to represent the number 2, handwritten 2. So to actually describe an image. So can we learn this latent space? How can we? So that is the idea. Why do we take care, or why do we want about the Z? So how can we learn this latent space is the question. That is done by the autoencoder. Okay. So now let us proceed. How do we learn this latent space after we take a break? Is that fine? Okay. 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 Hello. Ah. Sir, shall we start? Okay. Thank you. Where exactly we left? So we till now we learned what autoencoder does. So how can we learn this latent space on its own? Okay, so that is an interesting. Uh, sorry, sir. Not this. Yes, yes, yes. So we stopped here. How can we learn this latent space? Okay, so how can we means the network learn the latent space? So recall that in the beginning we were introduced that it is not a supervised problem. Okay, because we don't know the idea of class label. Fine. So we don't actually know Z. We don't actually know Z in the sense we don't know what set of latent variable we should extract. That we don't know. Whatever the network that produces is the right and it should be meaningful. Okay, since we don't know that Z, we cannot make sure that whatever the network that has been produced, the Z is meaningful or not. Somehow we have to verify, right? So we can't directly just apply back propagation because we don't know this target value. Or what I can say is that we don't know the class label or we don't know the value of Z also before. So since we don't know these two, we cannot apply back propagation learning algorithm as we do in neural networks, artificial neural network or convolutional neural network. But we cannot apply that here because we don't have the label information. But what we have instead, let apply a trick. We actually trying to reconstruct the original data. For that only we are doing the reconstruct process. Okay, so now what for we are reconstructing? Can anyone tell that? Reconstructing we do only to ensure that the Z that we have produced is meaningful or it is produced the right one by the autoencoder. Otherwise there is no point in reconstructing image, right? Because we have that images already in our hand. Okay, so that two we already have. What is the purpose of reconstructing two back when I have the original image? The reconstruction is required only to ensure that the Z that has been produced by the autoencoder is meaningful or not. Just for that purpose only we do the decoder. Other than that there is no more use. Is that fine? Okay, so train the model to use this feature to reconstruct the original data. So as a result, we have the decoder part. Okay, so the decoder part is required just to ensure that the whatever the Z, okay, latent variable that it learned is meaningful. Okay, decoder learns mapping back from the latent space Z to the reconstructed observation, which is X hat. X hat denoting the estimated or reconstructed version of the input data. So it is now possible, you can, now it is possible to measure the loss. How do you do that? Can anyone tell me? Earlier we could not able to do because we don't have the target value. Okay, generally we do the target value by taking the actual output. Okay, actual output minus target value, and then we will square the difference. Okay, and then we do for all the samples where samples ranges from 1 to n, 1 to n. So this is nothing but minimum square error function. Okay, now we have the input original image which is X and we have the reconstructed image. How do you measure the loss? Can anyone tell me? How do we measure the loss? No? Okay, let me look it in the chat. Are any answers? No. So how do we measure the loss? We have reconstructed image which is X hat, X hat denoting the estimated or reconstructed version of the input image. Okay, So now it is possible to measure the loss. Just take the difference between reconstructed image and the original image. Okay, so now that is possible, right? So now you take the difference between the x hat and then x, that can give us the loss. Okay, this is how you can learn the better representation of z. Fine. So how can we learn this latent space is the idea that we have discussed right now. So train the model to use this feature to reconstruct the original data. So when you do the reconstruction, if you can able to reproduce the data that is given to the network, then the job of autoencoder is done, or it has produced the meaningful z. If it is not able to reproduce, if it consisting of lots of noise, then this error, okay, this loss that we have computed, no, that will be maximum. Okay, that is getting as a feedback, and then it will try to reproduce the better representation. Okay, and this whole process now turns out to be supervised model. We, although we have beginning something from the super unsupervised mode, by introducing this loss term, this network turns out to be the supervised. So we can supervise this by basically comparing the output with the original image. Okay, the loss term can be used in back propagation just like before. As before, we can use that. Now we can see the shifting the problem from completely unsupervised problem, where there is no notion of the latent variable. Fine. So now we have some notion of supervising it. Although it is not supervising learning, but we can at least supervise by with the help of the loss, supervising it end to end. End to end we can supervise and then do that training process. Okay. This reconstruction loss is forcing the decoder to learn the most rich information, the most rich latent variable possible, so that it can describe the original image best as possible. Okay, so this loss function does not require any label. Now you see that we have not used any label. Okay, just we took the difference. So we are simply feeding it images of 2 or whatever the number. Okay, I mean, it will work for any number of images, handwritten images, number 2. So we are learning the underlying latent variables associated with this data. Okay, so we just learn those latent variables which are associated with the data by this way. So autoencoders background. Now you can see that now let just start abstracting away this image as little bit by removing all the convolutional layer. Okay, right now I have introduced with one or more number of convolutional layers. Now when we look at an abstract level, the autoencoder has the architecture of something like this. Okay, this actually hidden. This part is one convolutional neural network, and then this part is deconvolutional neural network to reproduce the reconstructed image, which whose size is same as x, or anything is fine. Whose size is same as x. Is that fine? Okay. So it is denoting we are going from this x to the lower dimensional z, and then going from z to a high dimensional, which is x hat. Okay. First, the encoder does x to z, and this z is lower dimensional representation, and decoder does from z to x hat. Again, this size is same as x. So this is transforming lower dimensional to higher dimensional. That's what it is mentioned. Okay, going from z to a higher dimensional space, which is x hat. So the idea of bottlenecking the network, okay, bottlenecking the network, forcing the information into the latent space, is essentially the idea of compression. Now you can see that actually this z is nothing but the compression form of the original image, which is x. Okay, so somehow autoencoder is so useful in reducing the dimension. So that is the one of the major application of autoencoder in computer vision. So if you want to reduce the dimension, you can straight away make use of autoencoder. Okay, this is the first application. Okay, very good. So autoencoder can be seen as a compression or dimensionality reduction. So now let us look what does that autoencoder does the compression. Now you can see this dimensionality of the latent space is this. Okay, dimensionality of the latent space is 2D and 5D. So this is the latent space dimension. 2D means only 2 dimension. 5D means 5 dimension. And then reconstruction happens with the help of 2D and then 5D. Now you can see this. These are the set of handwritten images which are represented with the help of 2D latent space. From that, when we reconstruct, you can see that all the numbers are visible. At least you can see that. But it is so blurred, you can say that it has some noisy, but you can read at least what the number is. Okay, when you try to retain with the more number of latent space, let's say 5. From 5, if we can reconstruct with the help of decoder, you can see that these information are quite visible. Actually, the noise is reduced. Now, when you compare this with the ground truth, you can see that this is almost have the high quality with the help of the ground truth. Is that fine? So it is just showing the original image, which is of nothing but 28 cross 28. Actually, this is of an MNIST data set. I will explain the description about the data set later on. 28 cross 28, which is actually 784. That 784 dimension is just represented with the help of only 2 and then 5. Okay, with only 2 and then 5, you can able to reconstruct lots of information. So that is where the power of autoencoder. Original image is nothing but 28 cross 28. Okay. So autoencoders for representation learning. A representation learning here we mean is nothing but the compression. So bottleneck hidden layer forces network to learn a compressed latent representation. Reconstruction loss. What reconstruction loss forces? Reconstruction loss forces the latent representation to capture the meaningful or rich information out of the input image that we see, or that input that we are given to the network. So auto encoding means automatically encoding the data. So this is called auto encoding. Okay, now let us quickly see the summary of auto encoder from the beginning, whatever we have discussed. Let us quickly summary and then give the important insights, difference between the auto encoder and with the PCA, because PCA also does the dimensionality reduction. So it is important to know the difference between the autoencoder and the originally uses for reducing the dimension, which is principal component analysis. Okay. So an autoencoder is a neural network. So when I till now I have not used the word neural network. I just make use of only network. That could be a convolutional neural network, that could be an artificial neural network. So now when we talk about an autoencoder is a neural network, because we have given only the trapezoidal shape, right? So what exactly that may go inside is actually abstracted somehow. Okay, but it is a neural network. Okay, one important thing, if you have only, if this is replaced by one input layer, one hidden layer and one output layer, then it is called under complete autoencoder. Okay, under complete autoencoder, which I have given in the beginning. But if you have one or more number of hidden layer, then it is just simply called as autoencoder. This is one major difference. Okay, what does mean by under complete autoencoder? But the job of that is that when you have input layer and then one hidden layer, this size, the size of the hidden layer should be lesser than the size of the input layer. Meaning the number of neuron in the input layer is larger in input layer, the number of neuron in the hidden layer is very, very less. Okay, and then when you do the decoder portion, it will just take this lower representation and then just to try to transform, which is same as the input image. So the same number of neuron will be kept at the output. If you have only one hidden layer, that is the best representation of this input image in the form of compressed image, or which is also called as latent variable. So this is called under complete autoencoder. Otherwise, it is just a autoencoder. This is the difference. Okay. So this neural network are subject to the task of representation learning. So it imposes a bottleneck in the network. The bottleneck forces a compressed knowledge representation of the input. Okay. This is all about autoencoder. Autoencoder is an algorithm. Okay. Sometimes they may call that it is an algorithm that code itself or that encode itself. Okay. And it comes under unsupervised learning. No class labels given during the training. This is all just a recap. Okay. When I give a recap, it is easy to uh, relook what we have seen from the morning. Okay. An autoencoder, when are you supposed to apply the autoencoder? Okay. So autoencoder is so suitable under the assumption where high degree of correlation are existing in the data. Can you tell why it is so important? Why this assumption is so important? What we are trying to do actually? Anyone? Okay. So what we are trying to do, because we are trying to retain the uncorrelated data. Okay. If the data is already uncorrelated, then there is no point in applying the autoencoder in that situation. So we just make sure that autoencoder will be highly suitable under the assumption that the data should consisting of highly correlated in nature. Okay. For uncorrelated data, compression and subsequent reconstruction would be difficult. So that is the reason. Okay. So this I can skip. Uh, we This part I have already explained under complete autoencoder. The number of nodes in the bottleneck layer, so this is called bottleneck layer, is less than the number of neuron in the input layer. Okay. So in that situation, if you have only one hidden layer, then it is called under complete autoencoder. Okay. Applications of under complete autoencoder, this is so important. Here, reconstruction is not our aim. As I mentioned, our job is not to reconstruct the image because we have the original data. Okay. We don't want the reconstructed image. So reconstruction is not our aim. We do reconstruct the input image from the encoded data. Okay. Just to ensure that encoding is done proper or it has produced the meaningful latent variable. Okay. For that purpose only we do the decoding part or we do the reconstruction part. So we are not interested in decoded part otherwise. So we are only interested in encoding part so that we can make use of these encoded data for other applications such as dimensionality reduction and then classification and clustering and so on. So from this input image, from the input data X to Z, once you can do the retransformation, this Z can be used for dimensionality reduction, classification, and then clustering. Okay. Actually, I don't want reconstructed image. Okay. Why do I want a reconstructed image when I have the original image? This reconstruction is done just to ensure that encoding has done proper. So that is all about autoencoder. Okay. Now, as I said that it is important to explore the difference between autoencoder and PCA. Okay. How powerful the autoencoder when compared to PCA. For that, here this some steps is given for computing the PCA. If you do not have an idea about how do we do PCA, you can, this couple of slide will actually help you. Okay, N is nothing but the number of sample. For each sample, we have to extract the feature xi, compute the covariance matrix, and compute the mean vector. and then define a transformation matrix S using eigenvector, and then we are supposed to find the top eigenvector whose eigenvectors are maximum. Okay, and then you can do the transformation like reducing into the number of a lesser dimension by retaining only the first two. Here we are just producing the top two eigenvector. So if the input image consisting of, let's say, 50 cross 50, the total number of dimension is 2500. From there we just retain only two dimension because we are taking the first two eigen value, lambda 1 and then lambda 2. Okay, so now let us explore the performance of autoencoder and PCA. Okay, now we will compare with the PCA. So now reconstruction happen using PCA for various PCs. PC stands for principal component from the original image 256 cross 256. This is 256 cross 256. Now you could see the reconstruction happens with one principal component. With one principal component, nothing information, I mean no information is visible. Everything is black. Okay, so this is of no useful. Now with the 5 principal component, you could retain as much information. 25 is also better, but you could see this 256 cross 256 is now represented with only 5 number of dimension. Okay, but that is the real power of the principal component analysis. Now when we compare which one is doing better, autoencoder, for that we have to understand the difference between PCA and then autoencoder. Autoencoder is the generalization of PCA. Okay, PCA just do the basic thing. Autoencoder tries to do more advanced feature. So what does that autoencoder can do something more. Okay, so given this point distribution of the data, which is represented in red color, okay, this red color line, okay, that is nothing but the PCA line. So PCA is the linear transformation. Okay, just does the linear transformation or mapping, that red color line, while the autoencoder is the non-linear transformation, which is nothing but the blue color line. Okay, so because of that non-linear function that the network supports, the autoencoder does the non-linear transformation of distribution. It tries to fit on the data which is non-linearly mapping. Okay, so let's implement a very simple under complete autoencoder for dimensionality reduction. If autoencoder uses only linear activations and the cost function is the mean squared error, then it can be shown that it's end up performing the PCA. Now I could just to highlight this. This is the code. Okay, this code is nothing but for autoencoder only. Okay, so autoencoder, as I said, that it consisting of neural network, right? Um, this is just an under complete autoencoder, meaning you have only one hidden layer. Okay, so you have mentioned the number of input layer here, number of input layer, number of hidden layer, and then number of output layer. And then you have mentioned learning rate, and then you have mentioned the shape. Okay, you have to reshape to initialize what X, and then hidden layer, fully connected layer. Okay, now you see that activation function is none. So when you replace the activation function as none, this autoencoder turns out to be PCA. Okay, when you have an activation function other than none, for example sigmoid, ReLU, leaky ReLU, then this under complete autoencoder turns out to be an autoencoder. Okay, only this important difference make a real power of PCA. PCA does the linear transformation, however the autoencoder does the non-linear mapping. Okay, the rest of the thing remains same. You have make use of mean squared error, and then you have make use of Adam optimizer, and so on. This is all about neural network, autoencoder using neural network. Okay, fine. So now let us see the experimental performance that is done for MNIST dataset. Okay, for MNIST dataset, that MNIST dataset consisting of 60,000 training images, 10,000 testing images. Image dimension is 28 cross 28. Dimensionality is going to reduce from 784 and then 784 to 2 dimension. And then the other important application is reconstruction. Reconstruction happens from 30 to 724. This I'll explain. These are the important applications of autoencoder in computer vision. Okay. Okay. So optimizer used Adam. Loss function is mean squared error trained for 100 iterations. Now this is an MNIST dataset. The MNIST dataset consisting of handwritten numerical value. Okay. 0, 0, 0. All possible 1. All possible 2. Some is written like this, some written like this, some written like this. Okay. These are the example. All possible handwritten of number 3. So if this is given, autoencoder converges to PCA. So now let us try to understand what does autoencoder tries to do. Now you see this activation functions of autoencoder is linear. Now here it is left. I mean they did not keep. Now you could see this same autoencoder we said, right? When you set the activation function as none, then it turns out to be PCA. Now they have did experiment for various types. Now they set activation function of autoencoder is linear. That means no activation function. It is kept as none. Okay, in that case it is linear. So PCA and autoencoder reduces to 2 dimension. Okay, now you see this from 724 to 2 dimension. It is reduced to 2 dimension. It can be observed that both PCA and autoencoder are identical. Can you see? The performance of PCA and the autoencoder are looks same. Why? Because here the activation function is none. It turns out to be PCA. So the job of PCA and autoencoder remains same. I mean it performs same. Autoencoder are more general than PCA because it can impose the nonlinear activation function. Now we will introduce some nonlinear function and then try to see the performance of the autoencoder. Okay. Now you can see deep autoencoder without any. Okay. Now you can see deep. Why it is deep? You have introduced more number of hidden layer. This is 1 hidden layer, 2 hidden layer, 3 hidden layer, and then this is last one, output layer. So there are 3 hidden layers. So deep autoencoder without any nonlinear function. Okay, there is no nonlinear activation function. Just they have kept as linear only, better than the shallow part. Now you can see that previously it is a shallow part because only one hidden layer which was under complete autoencoder. Now you have introduced more number of layer in between, right? So when you introduce more number of layer, now you can see that the performance of autoencoder is somewhat better than the PCA. Oh, sorry. This is also autoencoder. Now, two-layered autoencoder with a sigmoid nonlinearity. So this is actually under complete autoencoder, and this is the sigmoid as an activation function. Now you can see this deeper part is performing better than this because you can see other than this red color, this part, everywhere it is so clumsy. You cannot really distinguish what number it is. But you can see at least it is improving. This part, and then this part, and this part, somewhat it is improving. But it is not that much improving. So now you can see this is the shallow part, this is the deeper part. Okay. So the deeper part is performing better than the shallow part. Now both are autoencoder. Okay. Now here So this is the difference, deep autoencoder with the nonlinear function. So now you see, this is deep autoencoder without nonlinear function. Now this is with the nonlinear function. ReLU. And when you compare with the PCA, so PCA we have already seen the performance. Now you see this, there is a good separation happens. Okay, because you are introducing the nonlinear functions. Now you see, number one, number two. Okay, so you can have a decision boundary in between. So you can see as many number of decision boundary, and it does the correct classification of all the numbers. So you can see that autoencoder improves the performance in classifying the handwritten characters with the help of reduced dimension, which is Z. Is that fine? So that is the most important application of the computer vision of autoencoder. The second important application is that reconstruction. Okay, so it is also possible reconstruction from the latent space. Okay, actually this reconstruction somehow indirectly used in the variational autoencoder to generate the sample as similar to the input image, but I can give you the insight. Okay, how this is going to reconstruct the, how the reconstructed image actually helpful to get back the original image as similar to the original image. Now we can see this. You can see this, right? This is the original image, and these are the reconstructed happen with the help of autoencoder, and reconstructed happen with the help of PCA. Now you could observe that as compared to PCA, autoencoder does this reconstruction job very well. Okay, so this reconstruction actually helpful to generate more number of sample images. Okay, now you can see that reconstruction happen. So B is the ground truth, sorry, A is the ground truth or original image. B is 30 dimension autoencoder. This is 30 dimension autoencoder, and this one is the 30 dimension principal component. Okay, this is 30 dimension, this is also 30 dimension. Fine. Now you see that reconstruction happened with 30 dimension autoencoder, retain much information as compared to PCA. Fine. Okay, so I think I have come to the end of the autoencoder part. If there is any question, I would like to answer. I have given an insight of autoencoder and its applications. The first application is the dimensionality reduction, and the second application is nothing but reconstructing the back image. And we could extend for generating more number of samples. Any doubt? This is, you can ask question. Okay, I can browse whatever I like. Okay, if there is no doubt, you can ask your general question, because some of you working on, or some of you interested to work in the research field, some of you interested to register your PhD. So generally you can ask questions. I would like to answer that. Yes, sir. Yes, sir. So can you repeat the question? No. Actually, synthesized image, we mean generated image only. Synthesized image is nothing but we are extracting the data which is actually not a real image. That is called synthesis image. Since synthesis image is generated by the generative model, we can also say that it is a generated image. That's all. Actually, generating model are useful to generate the synthesized image. They interchange the terminologies, nothing else. I think I switched on my camera. Is that fine, sir? Yes. Because we can synthesize the image in a different way. Okay, so now people uh, people are heavily used generative model to synthesize the image. So that name synthesized image is replaced slowly by the generated image. That's all. Okay. Mm, mm. Okay, sir. Um, to my knowledge, that is the answer. Synthesized image are the images which are not real and that can be generated in several ways. Generative model is one of the way. Medical data. Okay. So medical data is so sensitive enough because if we have the record of the cancer, okay, for example, if we have taken the MRI images or any particular images which has the cancerous portion, okay. Now, when we are able to generate the synthesized data, okay, that synthesized data is actually not existing, isn't it? So, we just assume, we just make use of these generated images to increase the number of sample size. Because of that, introducing the number of sample size, it may lose the sensitivity of the data because it is not guaranteed that the same what is that same size of the brain tumor and then same location may occur for the rest of the patient because the location and the size may vary, right? So, it is so highly not recommended for the medical images, but it is okay to use for other applications like face recognition, gender recognition, or any other application which is not so sensitive enough. So, in that situations, one can make use of this data augmentation. But especially in case of medical field, it is so sensitive enough to say that suppose if the patient does not have any cancer, but if the system tries to say that it is affected with cancer, that is so sensitive, right? So in that situations, it is highly recommended not to use for data augmentation, that is upsampling the data. Instead, they are recommended to downsample the data. Meaning, if you have 100 normal images, 50 diseased images, instead of taking 50 to 100 disease images, you can reduce the normal images as from 100 to 50. So you have 50 normal images and 50 disease image. You can train with the you can train with the class imbalanced data, but in this case people also has the problem that the number of data sample is very less. So sometimes neural network requires more number of sample data to accurately produce the results. So it has both pros and cons, but we have to try to manage, especially in medical field, because it is so sensitive to say that patient which does not have any disease that it has a disease, and the reverse is also so sensitive, right? So if the patient is affected with cancer, but if the system or the neural network tries to detect that he is not, then there will be a delay in what is that treatment process. By the time that disease will become highly effective. So both are so sensitive. So we should be handle this data very carefully, especially in medical field. So people don't recommend just like to follow data augmentation for medical field. So this is the uh, an important note, and this is very interesting question. I expect that I should address this to the audience. Okay, sir. So any other questions? Okay. Okay, I think no questions from the participants. We can complete now, sir. Yeah. I will share the PPT for autoencoder and variational autoencoder. So you can share that with the participants. Thank you, sir, for providing the wonderful opportunity. Okay, fine. Yes, sir. Thank you. I'll share the variational autoencoder. That is also easy to follow. Um, okay. Okay, sir. Pleasure is mine. Thank you, sir. Thank you all. Have a wonderful day.